Keeping track of your money should be fairly straightforward, right? If you have more going out than coming in, you have a problem. And you will quickly see this in a shrinking bank account balance. Well, the way chemists track enthalpy changes in reactions is not so very different. And chemists keep tight records. This is Real Chem. You may have heard someone say, the energy is stored in the bond. This makes it sound like when you break a bond, it gives off energy. This is not really the case. It always takes energy to break a bond, and usually it takes a lot of energy. Tracking energy changes when we break or form bonds gives us a very clear picture of what is actually happening. Let's explore. Imagine holding two magnets that are stuck together. When you pull them apart, you can easily feel that energy was needed to do this. The same is true of chemical bonds. Breaking them requires us to put energy in. Bond breaking is always an endothermic process. Now, how much energy is needed to break different types of chemical bonds is well documented in widely available tables. What might not be so widely appreciated is that when atoms join together, energy is given off. Bond formation is always an exothermic process, and the tables give these values as well. For example, it takes 415 kilojoules to break 1 mole of carbon-hydrogen single bonds, or when 1 mole of carbon-hydrogen single bonds forms, 415 kilojoules is given off. We can estimate the enthalpy change for a reaction if we imagine that it occurs first by breaking the bonds in the reactant molecules, then forming the bonds in the product molecules. Using bond enthalpies from the tables, we can then calculate the overall enthalpy of the reaction. Take, for example, the combustion of methane. 1 mole of methane reacts with 2 moles of oxygen gas, forming 1 mole of carbon dioxide and 2 moles of water. Looking at the molecules, we see that separating the reactants into individual atoms requires breaking 4 moles of carbon-hydrogen single bonds and 2 moles of oxygen-oxygen double bonds. The energy needed to do this is therefore 1,660 kilojoules plus 996 kilojoules for a total of 2,656 kilojoules. When the product molecules are formed, 2 moles of carbon-oxygen double bonds and 4 moles of oxygen-hydrogen single bonds are formed. The energy given off is therefore 1,598 kilojoules plus 1,856 kilojoules for a total of 3,454 kilojoules. Now, since more energy is needed to break bonds in the reactants, which is the 2,656 kilojoules, than is released when forming bonds in the products, which is the 3,454 kilojoules, overall, energy is given off, and the change in enthalpy for the reaction is 2,656 kilojoules minus the 3,454 kilojoules, giving negative 798 kilojoules. And the net energy change is negative. The reaction is exothermic, and the energies of the products are 798 kilojoules lower than the energies of the reactants. And voila! We now have the answer to our conundrum. The energy of the product's bonds is larger than that of the reactant bonds, which means the product bonds are overall stronger than the reactants bonds. So it's not that energy is stored in bonds, rather, it's that the reaction exchanges weaker bonds for stronger bonds. It's the difference between the reactants and products' bond energies that matter. The chemical energy accounting we have followed here is not so different from your everyday management of your money. If you take out more than you take in, expect some negative values. And for your money, this is not good. It turns out keeping tight records matters for money and chemistry. So explore and remember to have fun.